What happens to a retired jet engine after its final flight? Inside its turbine blades is a metal so valuable that a single engine can yield over $500,000 in pure titanium and superalloys. But extracting it requires 1,000-degree furnaces, perfect alloy sorting, and zero contamination. Over 650 aircraft retire each year. The real treasure sits inside the engine. Every year, over 650 commercial jets are decommissioned. Hidden inside their engines is a secret urban mine, titanium and superalloys worth millions. But extracting pure metal from 2-ton turbines demands an industrial ballet of precision disassembly and 1,000-degree smelting. One contamination mistake can turn a fortune into worthless slag. Inside a decommissioned Boeing 747 engine, the turbine blades spin no more, but the metals they're made from are worth more than the aircraft itself. A single high-pressure turbine blade contains rhenium, a metal rarer than platinum that can push recycled alloy value to $32,000 per kilogram. And there are over 80 of these blades in just one engine. More than 13,000 aircraft will retire in the next 2 decades. Not just commercial jets, but military fighters and private planes. Their engines are the crown jewels of this urban mine. The fan blades at the front are solid titanium. The compressor discs are nickel-based superalloys like Inconel. The casing alone can weigh 2 tons. Yet, most people think old planes just rust in a boneyard. They don't realize that 90% of a modern jet is recyclable, and the engines are where the real money lives. The process begins not in a smelter, but on a dismantling floor. Technicians strip external wiring and electronics first. Then they begin separating the massive engine sections. Every piece must be identified. They use an X-ray fluorescence analyzer, a handheld gun that can tell you an alloy grade in under 3 seconds. Point it at a turbine disc, and the screen reads Inconel 718. A different blade might show titanium 6-4. This sorting step looks routine. It is not. Because here is the hidden danger. Even 100 parts per million of the wrong element can disqualify an entire batch from aerospace use. Mix a titanium blade into a nickel superalloy melt, and you don't get a hybrid. You get worthless slag. Factories have lost entire furnace loads because one mislabeled part slipped through. The sorting floor is where fortunes are protected and disasters are born. Once the metals are separated and verified, they head to the smelter. This is where the real transformation begins. Titanium requires temperatures above 1600 degrees Celsius, consuming 361 megajoules of energy for every kilogram produced. But recycling that same kilogram from scrap uses up to 95% less energy than starting from raw ore. The environmental prize is enormous, yet the margin for error is zero. And as the loading crew prepares the first batch for the plasma arc furnace, they must confront a terrifying truth. Inside one of these crates, buried among verified parts, could be a piece of metal that doesn't belong. The next 60 seconds will determine if the melt makes millions or becomes a 7-figure catastrophe. The furnace door seals with a hiss. Inside, the temperature climbs past 1600 degrees Celsius. The titanium scrapped begins to glow red, then orange, then blinding white. At precisely 1660 degrees, the metal collapses into a molten pool. The loading crew stares at the control monitors. The first 30 seconds pass. No alarms. But the real danger isn't the heat. It's what's invisible. Even 100 parts per million of the wrong element, iron from a stray bolt, nickel from a mislabeled blade, can poison the entire melt. Factories have watched entire furnace loads turn brittle and useless because someone, somewhere, touched a turbine disc with a contaminated glove. So the operator watches the chemical spectrometer readout with the focus of a bomb technician. The numbers tick upward. Titanium purity, 99.4%, 99.6, 99.8. The melt clears the critical threshold. Now the real refinement begins. Because smelting raw scrap is just the first step. To turn this molten mass into material that can fly again, the recycler must push the purity even further. This is where advanced technology enters. plasma arc melting fires a jet of ionized gas at the metal, superheating it to over 2,000 degrees. Impurities vaporize. Electron beam melting uses a focused beam of electrons to scan the surface, forcing out trapped gases and unwanted elements. Vacuum induction, refining, removes the metal from any atmospheric contamination entirely. Each process strips out contaminants until only the titanium and its intended alloying elements remain. The goal is to reach virgin quality ingots, material so pure it meets the AS 9100 aerospace standard. This is not scrap metal, this is strategic material, and the value jumps accordingly. A ton of unsorted turbine scrap might fetch a few $1,000s, but ingots certified for aerospace use can command 10 times that. The question is, where does all this scrap come from? And the answer will surprise you. Most people imagine the recycling yards full of entire gutted engines. Those do arrive, but they're a fraction of the feedstock. The real secret of the titanium smelter is that it feeds on a different kind of waste entirely. When aircraft manufacturers machine titanium ingots into fan blades and structural components, they cut away up to 90% of the original metal. That's right. For every 1 kilogram of finished aircraft part, 9 kilograms of titanium end up as machining chips, turnings, and offcuts. This manufacturing scrap is collected, cleaned, and sent directly back to the smelter. It never leaves the supply chain. It is a closed loop that operates in near silence, hidden from the public eye. And that loop is the pivot that changes everything. You thought you were watching the story of old jets getting melted down. In reality, you are seeing one of the world's most efficient industrial ecosystems, where the same titanium atom can pass through the smelter, become part of a 747, get machined down, return as scrap, get remelted, and fly again within weeks. The aircraft companies don't just recycle. They rely on this loop to survive. Without it, the global aerospace industry would need so much raw titanium that ore production couldn't keep up. The economics would collapse. But to keep that loop turning, the smelter must achieve perfection every single time. Because if one contaminated batch makes it into an operating jet engine turbine spinning at over 10,000 revolutions per minute, the result could be catastrophic failure at 40,000 feet. The stakes are not just financial, they are human. That pressure shapes every decision on the sorting floor, every temperature setting on the plasma arc, and every quality certificate stamped on the final ingot. And as the demand for lighter, stronger, more efficient planes grows, the pressure is only intensifying. Which brings us to the next revelation. The race to refine scrap is now a geopolitical contest, and a single breakthrough in melting technology could shift the balance of the entire aviation industry. The race to dominate the titanium recycling loop is no longer about environmental bragging rights. It has become a quiet industrial war fought in the shadows of the global supply chain. The United States, the European Union, and China all know the same uncomfortable truth. The metal that makes a modern jet lightweight enough to fly is concentrated in a handful of mines and a shrinking number of advanced smelters. Whoever controls the recycling technology controls the cost of building an air force or a commercial fleet. And that weaponization of the scrap stream is happening right now. Take rhenium. This rare metal makes turbine blades able to withstand temperatures above 1700 degrees Celsius without melting. It costs more than gold and comes primarily from Chile and Kazakhstan. When a jet engine recycler reclaims rhenium from old blades, they bypass a fragile mining pipeline that can be disrupted by a single diplomatic crisis. One successful melt of rhenium-rich superalloy scrap can be worth more than the annual revenue of a small airline. But the process is so delicate that only a handful of facilities on Earth can do it at aerospace-grade quality. Now consider the scale. Some specialized recycling firms estimate that procurement costs for new rhenium-containing blades exceed $7,000 per piece. Inside a single junked engine, there may be 80 of them. The math is brutal. Recover them correctly, and you generate millions in strategic material. Lose them to a sorting error or a contaminated melt, and you have destroyed critical national supply. Good luck buying replacement rhenium on short notice. This is where the story gets genuinely frightening, because the scarcity of these metals has created a new kind of black market. Counterfeit aerospace metals are entering the global supply chain. Scrap dealers, sometimes unwittingly and sometimes not, sell titanium stock that has been mislabeled, mixed, or deliberately falsified. There are documented cases where entire lots of so-called aerospace-grade titanium were later found to contain traces of aluminum or steel that made them dangerously brittle. In the worst scenarios, that metal could end up in a commercial airliner's engine, a military fighter's airframe, or a space launch vehicle. Remember the contamination threshold? 100 parts per million. Even a microscopic amount of iron introduced during smelting can change the crystal structure of a titanium alloy and cause it to fail under stress thousands of cycles earlier than designed. That is why the smelters we visited are fortresses. Every incoming scrap shipment is scanned and rescanned. The handheld XRF analyzers are calibrated daily. Any heat lot that shows a suspicious reading is quarantined and tested with mass spectrometers that can detect elements at the parts per billion level. Yet the traffickers are getting smarter. They coat inferior metals with a thin layer of pure titanium to fool surface tests. They forge mill certificates that look indistinguishable from originals. The people on the sorting floor are not just metal workers. They are frontline soldiers in a war against counterfeit that could bring down a plane. But the industry has a secret weapon. It is not a machine, exactly. It is a closed-loop agreement between the world's largest manufacturers. Rolls-Royce runs its revert program, recycling over 95% of its own manufacturing waste and used parts back into new engines. Boeing and Alcoa have a similar pact that recovers 8 million pounds of high-grade aluminum and titanium scrap every year. These circular economies create a chain of custody that is nearly impossible for counterfeiters to penetrate, because the metal never leaves the approved industrial family. The scrap from a Boeing factory floor goes directly to a certified smelter and returns as an ingot stamped with a digital birth certificate. This closed-loop model is the answer to the contamination nightmare. It is also the key to the future. The next generation of aircraft engines will demand superalloys that push the limits of metallurgy even further. Cobalt, tantalum, ruthenium, tungsten, these metals will be reclaimed not from mines, but from the engines rolling off runways today. The smelter is no longer just a recycler. It is the world's highest tech alchemist, turning yesterday's scrap into tomorrow's flight. And as you watch a freshly cast titanium ingot emerge from the cooling chamber, glowing with a pale silver light, you realize the full circle is complete. The very metal that propelled millions of passengers across the skies has been reborn and is now ready to carry humanity forward once more. That glowing ingot isn't the end of the story. It's the start of its next mission. Within days, it leaves the smelter bound for a forging plant where it's heated, pressed, and machined into a new fan blade. That blade undergoes ultrasonic inspection, X-ray scanning, and a battery of fatigue tests. Once certified, it's bolted onto a brand new engine destined to push a wide-body jet across the Pacific. The titanium atom that once screamed through the sky inside a 747 is now doing it again, refined, reborn, and indistinguishable from virgin metal. And that loop isn't just happening once. The same atom can cycle through the smelter 8, 10, even 15 times over decades. Each time, a fraction of the original machining scrap is captured and returned. The result is an industrial ecosystem where 95% of all titanium waste is recovered and reused. To put that in perspective, the average gold recycling rate is less than 30%. Aerospace titanium beats it by a factor of 3. This closed loop has quietly become the backbone of modern aviation. Without it, Boeing and Airbus would need to mine and refine an additional 1.5 million tons of raw titanium ore every year. The energy savings alone are staggering. Recycling titanium from scrap consumes up to 98% less energy than producing it from ore. That's the equivalent of taking millions of cars off the road permanently. And the environmental prize extends beyond carbon. By keeping rhenium, cobalt, and platinum group metals out of landfills and in active use, the smelter prevents habitat destruction from new mining operations in sensitive regions. But the most profound consequence is something few outside the industry appreciate. This relentless recycling loop has made high-performance aircraft more affordable, more sustainable, and, counterintuitively, safer. Because when every kilogram of recycled superalloy meets the same AS 9100 standard as newly mined material, the aircraft industry no longer faces the supply shocks that once grounded fleets and bankrupted carriers. The smelter has become a shock absorber for global aviation. And now, the technology born inside these jet engine smelters is spilling into other worlds. The exact same plasma arc melting and electron beam refining techniques are being used to reclaim titanium for hip implants, spinal cages, and dental prosthetics. That metal you are flying on today could be inside a surgeon's tray tomorrow. Rover missions to Mars use titanium alloys initially designed for turbine blades and then recycled back on Earth. The circle keeps expanding. But perhaps the most surprising detail is this. Your smartphone might contain aerospace titanium. High-end device frames increasingly use recycled titanium sourced from the same smelters we've been following. The metal that once carried 400 passengers across the Atlantic at Mach 0.8 might now be resting in your pocket, holding your screen together. It's a quiet testament to how the extreme demands of aviation create technologies that eventually shape everyday life. And yet, despite all this, the public knows almost nothing about it. The smelters operate behind fences and factory walls, their work hidden from view. The next time you board a plane, look out the window at the engine hanging from the wing. Inside it, the ghost of a retired turbine might be spinning. That's the invisible miracle of the jet engine smelter. That invisible miracle runs 24 hours a day, 7 days a week, in plants across the world. No headlines, no fanfare. Just metal moving from wing to furnace to wing again. And it makes you wonder, what else around you is secretly on its second or third life? The bridges you drive over, the buildings you work in, the satellites beaming this signal across the planet. How much of it came from something that already served its purpose once and was simply given another chance? The smelter doesn't care about glory. It just keeps turning waste into flight. And the next time you hear a jet rumble overhead, you'll know a truth most passengers never consider. Inside that sound is a ghost engine, still pulling, still powerful, still perfect. If this kind of hidden engineering fascinates you, hit subscribe. We're going deeper into the machines that move our world. See you in the next one.